In this video, we will discuss how to convert between one-line notation and cycle notation for permutations. We'll also prove that permutations of finite sets have a cycle decomposition. We'll finally finish by discussing my card shuffling problem. So in the previous videos, we discussed two different notations for working with permutations. One thing that we still need to discuss is how to convert between the two approaches, because it is possible to convert between them, and sometimes you have to be able to. So, how do you convert from a permutation in one-line notation to cycle notation, and vice versa? Well, remember that you're really working with this permutation here, and so you just have to ask yourself, what does 1 do? 1 goes to 3. Where does 3 go? 3 goes to 4. 4 goes back to 1. And so that finishes off the first cycle. Note, of course, order doesn't matter. We just pick 1 because, well, we're lazy and not original, and 1 is the smallest positive integer. We haven't finished doing the conversion, though, because we still don't know what happens to 2 through 9. So the smallest integer we haven't worked with yet is 2. 2 goes to 5. 5 goes to 7. 7 goes to 8. 8 goes to 6. 6 goes to 9, which goes back to 2. So that finishes off another cycle. 1, 2, 3, 4, 5, 6, 7, 8, 9. There were 9 numbers, and all of them appear, so we're done. That's the cycle notation for that permutation. And so that's the strategy or algorithm. You look for an element that hasn't appeared in any of your cycles yet. You look at it in the first row, you figure out what your permutation does to it, and then you look at what the permutation does to the next element, and so on until you complete the cycle. And that's how I figured out what the permutation did to 1 and then what it did to 3. Likewise, to convert back, I just have to ask myself, where does 1 go? Well, I look for 1 in the cycle notation. 1 appears here. What's to the right of 1? It's 4, so 1 goes to 4. You can, if you're actually doing this without writing the top row, the very next thing you'd ask is, where does 2 go? Since 2 doesn't appear, it must be a 1 cycle, so 2 goes to itself. Where does 3 go? Well, 3 is in this cycle. The next term to its right on that cycle is 1, so 3 goes to 1. Where does 4 go? 4 is in this cycle, so 4 goes to 7. 5 is in this second cycle, so 5 goes to 8. 6 doesn't appear, so 6 is a fixed point. 7 is in the first cycle, its right neighbor is 3. 8 is in the second cycle, its right neighbor is 9. 9 is in the second cycle, its right neighbor is 5. And so you can see that you can go back and forth between the two notations. I should mention this advantages of each approach. I've already mentioned before, the one advantage with one-line notation is that there's a unique way to write down your permutation, whereas I've already mentioned before with cycle types that you can write more than one version. But there is an advantage for cycle notation over one-line notation, is that this one-line notation is relying on the fact that we have an order on our set, that we have a first element, a second element, and so on. So you have to fix that ordering both to write down the one-line notation and to write down this conversion back and forth. So if you're working with some collection of objects where there is no natural choice of ordering, it's hard to figure out what to do. Whereas a cycle notation, it's always clear what to do because it doesn't depend on order at all. So this conversion algorithm actually leads to a theorem from the book that I'm going to state as a fact. Every permutation in a finite symmetric group can be decomposed into a finite product of disjoint cycles. So we already talked about cycle notation, but one thing I didn't prove was that every permutation actually has a cycle notation. And so I'm not going to give the full proof because it's in the book and the proof is actually somewhat tedious, but I'm going to describe the algorithm. And so the proof is essentially showing that the algorithm works, and it's a bit of a pain. And so here's how the algorithm works. You choose an arbitrary element in your set, and you define the first cycle to be I, sigma squared of I, and so on. You know this cycle is going to have finite length because you're not working with an infinite set. So you know eventually you're going to close off and repeat yourself. Let N1 be everything that's not on that cycle. Now choose an element in your leftovers. Let sigma 2 be the cycle generated by that element, namely that element, sigma of that element, sigma squared of that element, and so on. Yet again, this cycle is going to have finite length. Now let N2 be your new leftovers. So you've removed from N1 all the elements of this cycle. Keep doing this. As long as you have elements remaining, take an element in your leftover set and create a cycle using it by looking at it, its image under your permutation, so on and so forth. This is always going to be a cycle of finite length. And so as long as these sets are non-empty, you're always deleting something. And so you're going to get a descending sequence of proper subsets. And so eventually you're going to run out of leftovers. And so once you hit that point, you now have a bunch of disjoint cycles. And why are they disjoint? Okay, that part needs a little bit of an argument. But it's at least clear that you have written sigma as a product. You at least have these cycles. So the only thing you need to claim is that sigma is a product of these cycles and they are disjoint. And why should they be disjoint? Well, I guess there it would be enough to just point out that, let's see here, sigma j to the k of I must be an nj for all k. That must be true. In other words, that whenever you create one of these cycles, the other elements on this cycle must also be in your leftover set. Why must that be true? Because if sigma j to the k of I were not, it still has to be an element of n, then you would have sigma j to the k of I has to be on one of your earlier cycles. Here, let me give myself some space. You'd have sigma to the k of j of I is an element of an earlier cycle. But what would that mean? That would mean that you would have, I should probably be using I sub j, right? Because that's the notation we're using. You would have that this permutation, this cycle, this kth power of this element is equal to something from an earlier cycle, some earlier power. K prime is just some integer. J prime is strictly less than j. But note that the way this is defined, that means sigma to the k ij equal to sigma to the k prime ij prime. And it's not too hard to get the contradiction here because, well, one of these two integers is smaller than the other. So if you invert enough, you now get that ij is sigma to the k prime minus k of ij prime, which would tell you that ij is on the cycle. Which is a bit of a problem because that would tell you that ij is not an nj. So in other words, the problem here, since sometimes a pictorial representation is a lot more helpful, as we're saying, suppose that I tried creating a cycle, but it turns out it looped and got an element from an earlier cycle. Then what we're pointing out is that, well, this contradiction argument is pointing out that this element right here also was on the earlier cycle. And this element was specifically defined to be in this leftover set. So you run into a contradiction because you specifically chose ij to be in here to begin with. Ergo, it must be the case that every element in this cycle is not in the earlier set, which is what I wanted to show. And then, of course, by definition, we actually defined nj plus 1 to guarantee that these elements were not an nj plus 1. And in fact, this set difference is literally the elements on the cycle. And so in particular, you've actually partitioned your set into disjoint subsets. And so that means every element on the elements on each cycle is disjoint. Note that even this part is not complete because all I managed to show is that the cycles are disjoint. You also still need to prove the other part, which is that sigma is a product of these disjoint cycles. And at that point, I think I will emphasize that the proof in gory detail is in the book. I mean, the rest of the proof is just pointing out that these two things are equal for every element j. And how do you prove that? Well, j has to appear in one of these sets. You restrict your attention to that set. You note that j is fixed by all of these cycles except the corresponding cycle you care about. And so that's the only cycle you have to pay attention to. And then on that cycle, j goes to the same thing that sigma j. J actually goes to sigma j. And so it is actually true. And the corollary of the proof, or the algorithm, is that you do in fact get commutativity when cycles are disjoint. So when you have your permutations written into cycle decompositions and the cycles don't have any elements in common, they can commute with each other. It's only when they have an element in common that you can't actually say sigma 1 times sigma 2 equals sigma 2 times sigma 1. Alright, so now let's go back to my favorite card deck problem. Here is the deck of size 6. Here was the permutation we wrote down. Here is the cycle notation for it. And so from the cycle notation, you can see it must have order 4. Because if I square, 2 is going to go to 5. That's not the identity. If I cube it, 2 is going to have to go to 4, which is not the identity. So if I take it to the 4th power, 2 is going to go to itself. 3 is going to go to itself, 5 is going to go to itself, and 4 is going to go to itself. So you have to shuffle a 6-card deck 4 times to get everything with perfect ruffle shuffles to get everything back in the original order. So naturally, you'd assume a 52-card deck takes more. But it turns out if you write down the cycle notation, it has 2 1 cycles, the first and last card, 1 2 cycle, and 6 8 cycles. And so, just to get an idea of what one of the 8 cycles looks like, let's look at 2. The second card ends up going in the 3rd slot, which ends up going to the 5th slot, which ends up going to the 9th slot, which ends up going to the 17th slot, which ends up going to the 33rd slot, which, if I remember correctly, ends up going to the 14th slot, which ends up going to the 27th slot, which ends up going back to the 2nd slot. By the way, the trick I'm using here is that when you've got a 2n card deck, when I is less than or equal to n, sigma of I ends up being 2i minus 1, and when I is bigger than n, sigma of I ends up being 2 times I minus n. You can actually check that it tells you the exact location of the ith card after a perfect riffle shuffle. Amazing that you can get a formula for it, but you can. And so the point is, if I square the permutation, 2 goes to 5. If I cube it, 4th power, 5th power, 6th power, 7th power, I need the 8th power to fix 2. And you can see that the 8th power fixes all the other elements as well. And it fixes all the elements on all the 8 cycles. And the 8th power also fixes the 2 cycle. So once you've shuffled the card deck 8 times with 8 perfect riffle shuffles, you will have completely reordered the deck back to its starting order. A clever student might note the way this ordering works. You order it so that the top half of the deck, the top card ends up on top, and then the bottom half of the deck, the bottom card ends up on bottom. They call this an in shuffle. There's a corresponding thing called an out shuffle where you don't have that property. For the corresponding out shuffle, you actually do have to shuffle the card deck 52 times. It ends up being one long 52 cycle. So now, if you spend your whole summer learning how to do perfect riffle shuffles, you can start to do magic card tricks involving shuffling 8 times in a row. I guess you could say that this stuff is not completely useless, but